So this will be a quick tour of the hardware for what's become my 6-letter word sculpture. You can see the 6 B7971 Nixie tubes there with the clock displayed. It's 2:18 and 41 seconds at this point. I'm using the EasyPick Fusion 7 development board along with the Pro C compiler for PIC32 is my development platform. If you look up a Microe, M-I-K-R-O-E, on the web, you can find their tools. Quick look at the hardware here. Of course, we've got the PIC processor sitting here. It's a 32-bit PIC. I'm using one of the UARTs here, so this has got an RS-232 to USB adapter here as a debug port. This is simply just providing debug output to a terminal session. This is the USB connection for the ICD and the programmer that connects the board to the main development environment. I've got a motion sensor down here that's hooked up to, in this case, it's driving port A bit 7 here, and with port A, of course you can't see the LEDs here, they don't show up. With motion, the output becomes a 1, and that 1 tells the clock there's somebody in the room. If it's 0 for 60 seconds currently, it'll basically blank the tubes, as it just did. Actually, it's not running for 60 seconds. I'm not sure why. I just put the code in place. I'll have to check it out. I've got a jumper set up here where I can select various modes to kind of demonstrate the system. Over here we've got the 6 DC to DC converters that are providing the 170 volts. For the Nixie tubes, there's 6 converter boards here, 1 for each tube. That's because the tubes can draw upwards of 30 milliamps with all the segments lit, and these are good for about 30 amps or 30 milliamps of current. There's a Rigol power supply sitting here in the background that's providing the +5, and in this case 17 volts to the up converters, or the little boost converters. Anyhow, we'll look at a couple of the modes here. In this case, it's just simply showing time. I can move this jumper down here, take a different bit low, and that puts it in the 6-letter word mode. So what it's doing here is randomly picking a 6-letter word from a list of about 21,000, and then randomly displays it 1 letter at a time. Of course, as I say that, it actually displays them in sequence. That was quite interesting. Kind of an interesting little coincidence. You can see the fade effect, so primps, I'm not sure what that word means. These are smart socket boards back here, 1 per tube. Each one has a PIC processor on it that controls the font and the effects. I'm using a fade effect to fade from the space to the letters. And then when it's done displaying it for a few seconds, it'll fade it back out to black and pick the next word. I can also, down here, move the jumper to another mode. Should be that position, and this is going to scroll by, as you can see, the date and the time. So there's a fair amount of code behind this. It's broke up into several libraries. We're going to move forward into looking at the actual code behind the scenes here. Let me get back to the 4-letter word mode just because I prefer that. And of course, the jumpers down here is just for demonstration purposes at this point. A couple of things to note: the random number generator seems to be extremely nonlinear. Large numbers of letters are repeated over and over and over. I've actually got code in place that forces it to go through the entire word library, then resets, and so it randomly picks words, but if that word's already been displayed, it'll either move up or move down through the list to find one that hasn't. That was, of course, taken care of in C code. The other thing you probably can't see down here, and again, it doesn't show up. It's kind of flickering there. I don't know if you can see RB0 there flickering or not on camera. Every time the interrupt occurs, that LED is toggled. In the background on this is, of course, there's the RealTime Clock module built into the PIC. Every time an interrupt fires, I think it's currently set at 50 milliseconds, it might be 25. There's a structure in the C code that has all of the date information. That structure's updated. If there's actually a time change, such as the seconds change, there's actually a flag created in there that'll tell the code written to look at that structure that there's been a change. So when I'm sitting here in the time mode, the time's only updated when there's actually been a change, so it's not rewriting this over and over. So the code actually looks for a change and says, oh, there's been a change, display the new time. That interrupt that's firing down there, and again, maybe you can see it here on camera, is really the heart of the system. So it updates that time structure. It also is what's taking care of sampling the motion detector code, and if it thinks there's been no motion, it'll time out and blink the tubes. So let's go ahead and take a look at the time setting function. I've got the clock here, of course, in the 4-letter word mode, or 6-letter word mode. The 6 buttons down here, actually 7 of these 8 buttons down here, are used to set the time. Bit 7, enter setup, and then bits 0 to actually that's not true. Bit 6 enters the setup mode, and bits 0 through 5 are used to increment or decrement various pieces. So if I go ahead and enter setup mode, it'll tell us, set up the time. It'll show the current time, and of course I can increment or decrement as needed to, hours, minutes, seconds, etc. I can then move on to set the date. Of course, it shows us the format, and here's the date, and I can, of course, increment or decrement months, days, the year there, etc. Then it wants us to set up the day of the week, and it's currently Saturday, and of course I can change that as well. And then I press setup one more time, it'll tell us to press setup to start, and it'll show us the current time it's set to, and when it is that time, I can then press start, and the clock is now running, and time started, and then it'll return back to whatever it was doing before. So the interrupt handler takes care of sampling the setup button and entering setup if needed. So anyhow, I think there's a brief overview of the hardware and the code as it currently looks, and from there we'll dive in and take a look at the source code. So we'll start looking at the code with the actual main function here. It's in a file named int2.c. This actually got copied forward from a different project. Apologies for the toenails clicking in the background. Every time I start to talk, the dog has to walk. Anyhow, we include the standard library since we're going to use various string functions. We've got a little library that I call the debug console that simply opens up a serial port in the PIC and gives us a function to write strings out to it. We have the smart socket library, which has all of the various functions for dealing with the smart sockets. Set time is a library here that simply is used to set the RTCC clock. We have the RTCC refresh library. This establishes an interrupt. That interrupt, as I explained earlier, fires on some interval. It updates a structure in memory that has all the things you need to know about time. It checks to see if you want to enter the setup, and it takes care of blanking the tubes if there's been nobody in the room for a period of time. 6LW.H implements the 6-letter word stuff. It's got the 6-letter word list in it and various functions to deal with that. And we just have some constants here for the smart sockets. There are various strings that set effects and that kind of stuff. Our C code here is really pretty easy. We've got a generic string here. Is it even being used in this code? I don't even think it's being used anymore here. So let's go ahead and comment that out. I don't think that's required, and do a build. Yeah, that was there for some debug and other stuff. That doesn't even need to exist anymore. We have a short variable here that returns to us the time interval between interrupts. The code allows you to set that to various intervals, 25, 50 milliseconds, etc. So that'll tell us what that interval time is. Standard kind of stuff you see here in the library. All analog pins are set to digital. RE9 pin is input. I'm not even sure why that's required in here. Tri-state A, so port A is input, port B is output, and we set all the port B bits to zeros. The interrupt handler toggles the least significant bit on port B. So you see an LED essentially blinking. We looked at that a little while ago. This is, of course, redundant with a bit of code down here. That can go away. Again, it's always good to kind of talk this stuff through because you find the stuff you can clean up. I currently have UART2 hard-coded to be my debug UART. DB initializes the UART, and then you can use DB write or write line to write to it. So let's go ahead and look at the debug console C code. It's pretty straightforward. In this case, DB init simply initializes UART2 at 460K baud. It's the fastest I could get it to go. Waits 100 milliseconds for that to settle down, and then DB write sends a string out the UART, and write line sends a string followed by a carriage return line feed. This, of course, could be any UART you wanted to use. I just picked two. Say there's not much here. This just kind of made it a little bit easier to deal with. Smart socket init is more complex. Let's go ahead and look at the smart socket C code. Let me open it up. And this is the smart socket C code. It needs to know about several things. So it needs to understand the PIC32 RTCC handler. It can provide debug, so it's got the debug console included, and there's a bunch of constants that I talked about earlier. We can tell it which UART to use here by undefining the particular line we want. In this case, I'm using UART6 to talk to the smart sockets. This library is hard-coded for 6 sockets. I've got 6 tubes. If you had 8 sockets, you would need to add additional spaces like in these strings here to deal with it. I didn't make it super generic. Rosie, please, I'm busy. She's so demanding. These are generic messages that can be sent. The idea here is you can modify these if you want to in memory. So $B7 is the initiator for a smart socket command. This letter here, then the next letter is the actual command. F for font, E for effect, S for speed messages, M for an actual message, U for underlines. And then there's, in this case, 6 zeros here. So the idea with font messages, if you wanted to mix fonts, you could replace those characters with the font numbers. The same is true for all of these. This text message gets used a lot here. Like if I'm going to display the clock, I'll put in the hours, minutes, seconds in here, and then output that. Last message keeps track of the last M-type command that was sent to the tubes. This is used if the tubes have been dimmed or have been turned off because of inactivity in the room. The tubes aren't actually shut down. The code just sends all spaces to them so nothing's displayed. When it detects that you're back in the room, it'll then reissue this command here to get whatever message was on them back. There's a global or a flag in here called Smart Socket Control Timeout Enabled. If it's 1, the timeout code's active. If it's a 0, it's not. There's the timeout counter. This is a down counter. When this counts to 0, the tubes have timed out and don't display anything. There's a timeout period here, which is the reset value. So if the tubes have timed out and then you come back into the room, it'll set this down counter back to this value as long as you're in there. This value is calculated on the fly depending on the interrupt speed and how long you want the timeout to be. And then a generic flag that says the tubes are enabled or not. And I've got a typo there. A little spelling error. So that will, of course, create an error. So we have a function here that enables timeout, the number of milliseconds you want the timeout to be. This is a long, so it could be like 60,000 for 60 seconds. And this is passed in as the interrupt interval time, and that gets passed out of the interrupt code that sets up the actual interrupt. Do a quick calculation to figure out the timeout period, set the down counter to the timeout period, and enable. In here, we go ahead and enable that the tube. I don't know what to call it here. The tubes can be disabled. We can disable the timeout. Code here to process the timeout. In this case, the sensor that I'm using for person in room is coded to port A bit 7. So we just go ahead and retrieve that bit into PIR here. If tube timeout is enabled, we check the PIR bit. So if it's a 1 where somebody in the room, and let's see, I haven't commented this yet, and the timeout counter is at 0. So if we've timed out, blank the tubes, and somebody's come back into the room, this gets us displaying again back from disabled. We set the counter, the down counter, back to the maximum period. We re-enable the tubes, and we take that last message I messaged and put it back on the tubes. If the timeout counter is non-zero, we decrement it. We make sure the tubes are still enabled. That's kind of redundant. Otherwise, we disable the tubes. So really, all this deals with is timeout of the tubes if the timeout function is enabled. This code here writes a string to the smart sockets. A string is the command to send to the tubes. This is no longer true. It's from a previous version. So it's just a simple function. It gets passed a character string. It checks to see if that fourth character is an M. In the command, the $B7M, if it is, it captures that last message that was sent that has characters to be displayed. If the tubes are enabled, we looked at this up here with which UART you want to use. It'll simply do a UART write with that string. Else, it sends out a string that says all the tubes are off. If we actually take a second here and look at smart socket constants, we'll find a constant here that's tubes off, and that is simply the $B7 preamble. It's a message to be displayed and 6 blanks. So tubes off in this case will turn all the tubes off, and of course this ends with a return. And these smart socket code themselves, the code that's running on the PICs and the smart sockets, is looking for that /R to say there's been a command terminated. Parse the string, and if it's something you recognize, execute on it. Again, this is pretty straightforward. This just resets smart sockets back to a default state. So font 0, underlines are off, effects are off, speed is off, and anything that's previously on the tubes has been they're all blanks at this point. So it just simply resets back to a known state. The smart socket initialize function that we saw called from the main code here, which is this line right here, smart socket init. Configures whichever UART we have defined to use. It's 9600 N81. It disables the timeout. It wakes up assuming we don't want the timeout running. 100 milliseconds for this to settle down. Calls the reset function to get the tubes to a known state and done. This is a bit of code that will take a wide string and scroll it across the tubes. You kind of saw that when I had the time date scrolling across the tubes. You pass this a string and pause time in milliseconds between each step. This is kind of an ugly function the way I wrote it, but it was meant to be readable and not necessarily elegant. There's a buffer that's created that can hold 512 characters plus 6 blanks on the beginning and end. So the idea is you copy the message to be sent into this buffer. You put 6 spaces at the beginning of the buffer, this code right here. You copy the string into the buffer. You put 6 spaces after the string you send in, and then you terminate the byte, and then you just walk through outputting that. Command is the string we're sending to the tube. We're just simply taking the ASCII characters and putting them into these 6 positions here, sending that command to the tube. Smart Socket write that string, and then we have a variable delay here where you can set the delay you want. Those comments really are no longer needed. There's a function here to display the current time on the tubes. It requires, like it says, the PIC32 RTCC header. This again creates a text message that it's going to manipulate here. I don't think the string variable is needed anymore in here. Oh, it is because of the debug code here. So what this code does is go to the current time structure that I've mentioned, we'll look at later, and pull out the time underscore member of it. Time underscore member is an exact copy of the bit fields from the RTCC. That's a BCD packed value. It's 32 bits wide. The most significant byte is I believe year, then month, then day, and then the least significant byte isn't used. So it goes ahead and grabs that value and formats it just to output it to the debug console saying the current time is, and it's showing us basically a BCD dump of that. Because this is encoded in BCD, it makes it pretty easy to manipulate. So we're just simply shifting the current time into the appropriate field and then adding 48 to it. 48. They're numbers. So this is going to be BCD packed from 0 to 9, and by adding 48 to it, I convert it to an ASCII 0 to 9. Packs these 6 bytes right here, writes it out. I'm sitting here wondering why there's this RTCC dump time command here. And that may be some redundant code. RTCC dump time, let's look at what that is. Oh, it's the header file. That doesn't do me any good. RTCC dump time. As you can tell, I have not spent a lot of time inside of this code. All it does is write debug information out to the debug console. That's really not needed in here. And I'm going to remove that because it's essentially redundant with what's going on up here. It was just a debug code that was injected at some point. I have a similar function for putting the date on the tubes, very similar. And then we have that long date time, which basically produced that scrolling string where it said Saturday, May, you know what the date was, 2018, and the time. And this is just basically in that structure I talked about is a pointer to the current day name, month name, the day medium length. So Saturday, okay, so Saturday, this would say Saturday, this would say March. Day medium is essentially, for this it would be 25th or 26th the 26th, etc., and just puts together a string and then sends it to that scroll function. In this case, we go ahead and write that string out to the debug console. Oops. Having a hard time getting the mouse clicks here up against the edge to get the cursor to show up. We go ahead and turn off effects. We actually need to do one more thing here for this to work. This is actually a defect that I chased earlier. We want to send the tubes off, string. So what happens here when you write to the smart socket tubes is I've told it to turn the effects off, but those effects are not disabled until the next time it's told to display a character. So by telling it no more effects fades and things between values. And then telling it to turn all the tubes off puts this in effect. So we've now got the effects off, and that way when the string scrolls, the effects aren't applied. Simple function here to set which font we want to use and which effect. And that's really it. So as you can see, this is just really essentially manipulating strings such as these and spitting that code out of an RS-232 port. Let's make sure we haven't broke anything by compiling here, and we have. That's interesting. What did I do? SS tubes. Oh, it's because I had misspelled. I had that typo above. So I correct the typo. Enabled AB LED. And that should now compile clean. I, of course, get some suspicious pointer conversions in there, but that is what it is. So we've taken a quick look here at the code that gets the tubes initialized. The next thing we're going to do is we're going to initialize the real-time clock calendar. And this can be called two different ways. It can be called with a BCD packed time and date to set the tubes to. So this would set the time to 6 p.m., 21 minutes and 0 seconds, to 2018, 5th month, 18th day, and the 5th day of the week. If you simply pass it all nines, it says don't change the current time date settings in the RTCC, leave them alone. This function returns the interval in milliseconds between each interrupt. So if we go ahead and look at the RTCC code, commented out here is a copy of that structure that we talked about. So there is this structure that has all the time information in it, the seconds, minutes, hours, days, month, week, day, and year. These get picked up directly from the RTCC, so the time underscore and date underscore are copies of those registers. This short time updated is simply a flag that when this structure gets updated, it's set to a 1, so that something external can say, oh, the structure changed, I need to do something. Used to detect seconds rollovers. Yeah, this is the previous seconds that was displayed, so that when this second changes, it knows to set this flag, and then it's got character pointers to these various formats of days and times. Got set time, set date, get time, get date, dump time. So RTCC initializes, as we looked at before. This gets passed in the time interval that we want the tubes to time out on. Let me step that back. RTCC and it's passed in the current time and the current date to set the tubes to. Remember, if those were all nines, we don't do anything. We do several things here. You'll find this in various places. We need to enable a secondary oscillator. We give it some time to come through. We wait till the bit changes. We put out the unlock procedure to these variables. And essentially, this is documented other places. We walk through and get to the point where we can actually set the RTCC, the time and date that came in. So if we look at RTCC set time and set date up here, which we'll find. So there's set time. If the incoming time is not equal to this, then we force the RTCC time register, and the same thing with the date register to be the passed in values. We set current time .seconds to 99 to force on the next second change. But there's been an update. We turn back on the RTCC. We wait for the bit to clear. Then we initialize the timer, RTCC init time. Initialize timer 1, and that code lives in RTCC refresh. So let me scroll up to the top here. We can pick an RTCC refresh variable by uncommenting the line we want, 25, 50, 100, 150, or 200 milliseconds. I'm currently using 50 milliseconds. so that init timer 1, this code's actually exposed. This sets up the appropriate variables to get a timer that's clicking every 50 milliseconds. I think I got this. I used the micro time calculator. You can download it from their site to actually come up with this code stub to put in here. You just put in, you want 50 milliseconds, timer 1, and it gives you these values. And let me come back over to here. So we have initialized the timer, and we've enabled interrupts. And we just return RDCC. Oh yeah, this returns the that 25 milliseconds, 50 milliseconds, etc. Just returns back that time that the interrupts are firing at. So if we go back and look at init timer 1, that'll get set up. We have defined a timer interrupt here. It's using the it's interrupt 7. It's the highest priority interrupt. So when timer 1 gets started, this interrupt will start to fire. This is using the hardware register pair so that we don't have to manage saving and restoring registers ourselves in software. And this is just a really standard little interrupt timer. In this case, we toggle that LED I talked about, so bit 0 on port B just gets toggled so we know it's fired. We look at port A. We'll look to see if that bit is low. So we mask everything off. And we look to see if it's 0. So if there's a 1 there, there's not. If there's a 0, we go into the set time function. Else, we call the RTCC refresh time date. This function simply updates that structure. And then we do the processing for the timeout to say should the tubes be disabled. So really that's the heart of what's going on in the background. It's fairly straightforward, I believe, if you've kind of read up on this stuff. So we've got through the code here where we've initialized the real-time clock using whatever values were last in it. We're going to enable timeout for the tubes. So we're going to do a smart socket enable timeout. I want it to be every 60 seconds. That's expressed in milliseconds. And I'm passing this value here, which is the number of milliseconds to an interrupt fires, into the function so I can calculate that down counter. Got some commented code out here that could display a time date stamp. We seed the random number generator. I'm trying to seed it from the real-time clock. Get the time, shift it down. I'm going to code this a little bit different. Shift it down 8 bits because those least significant 8 bits are always 0. It's no different than dividing by 256. I just think it reads better. And add to it the date, and that tries to randomize the real-time clock. We then fall through, we're going to initialize the 6-letter word code engine. That's actually all lives in a header file. I haven't broke this out. So we have a function here, or a code block here that it implements the 6-letter word function. It makes use of, again, of various headers that are needed here. There's 22,157 total words that I downloaded from this website. We're telling the system there's that many words it can deal with. We have an array here of that size. Currently, jump one is shorts. This is pretty wasteful, but it is what it is. That when a random, when a word is displayed, the position in this array here will be set to a 1 to tell us it's been displayed. And we have a displayed count that tells us how many unique words have been displayed. And these are used to deal with the fact that the random number generator isn't linear at all, and that it provides the same numbers over and over and over. We have this huge set of code here. It is a constant code unsigned character. The constant code is important because that piece there puts us into the ROM on the PIC32 and not into RAM. There's not enough RAM. This is about 120K of data. It is 6 times 22,157. So 120, 130K bytes of information. There's enough room in the ROM. I think there's 512 megabytes of ROM in the PIC32 I'm using. I could be wrong. There's enough ROM in there to store this. So this is kind of ugly. We get down to the bottom of the list of words. We've got a function here for clearing that displayed array out. Basically what happens is if we've displayed every possible word, then we set that array back to all zeros so we can start displaying words again. When we initialize the 6-letter word code, that's what we saw called from my main. This just simply gets everything cleared here and ready to rock and roll. We can do a 6-letter word pick. That'll return the index of a word. The displayed count is incremented. If displayed count is now equal to the total number of words in the array, we know we've displayed every possible word. So we go ahead and clear it back to open the array up again so we can display words. We get a random index position, and we'll keep trying until we get a number that is less than 6-letter word count. We check that array to see if we've previously displayed that word. If the least significant bit of the random number appears a 1, then we're going to look up through the array for the next word we find that hasn't been displayed, and we'll wrap around to 0 if we need to, and this will work through the array until it finds a word that's not been displayed and return it. I'm toggling B1 here on port B. That tells me this function was entered. And I'm toggling B2 here to tell me that this function was entered. And this function is the same as this one, except that it decrements. So if that least significant bit is a 0, it'll walk down. So sometimes it'll walk up through the array looking. Sometimes it'll walk down. We tell it that that word position has been displayed. We return a pointer that points into this character array to the first letter we want to display, and that's what the multiplying by 6 right here does. And we return that pointer. And the reason it gets multiplied by 6 is if we picked word 0, we return a pointer to this character right here. If we returned word 1, we need a pointer to this character. So 1 times 6 gets us pointed to here. Word 2 times 6. Oh, that's actually an interesting bug. 6 is 12. No, that's correct. 1 times 6 is 0, or 0 times 6 is byte 0. 1 times 6 is position 6. 2 times 6 is position 12, which would be here, etc. So that multiplying by 6 points us to the first character in this list of words. And then while to go, actually I just fell at the bottom of this. We then have the 6-letter word display function that'll take that 6-letter word and display it on the tubes. So we start out again with a command that is the message to display bytes. In this case, they're set all to spaces. We know that there's 6 different letters we want to expose here. We call the function we just saw above to pick a word to be displayed. I go ahead and write that word out, or actually the index position to the word out. I then load a string up with the 6 letters of the word we want written, and I send that out. So this is really all debug right here. It's telling me the index and the 6 letters represent the word. And then while to go is not 0, so remember to go says we got 6 letters to display. We generate a random number. We go ahead and truncate that down to a 7, which is the least 3 significant bits. And if that's less than 6, it's going to represent 0 then to 5. It'll expose the letter in that position, assuming it hasn't been exposed before. If it hasn't been exposed before, it decrements to go. It exposes that letter, writes it to the tube, and this will just sit in loop until all 6 of them have been displayed. We leave it on the tubes for 5 seconds, and we return. And that's really the heart of what we just looked at right here. So we're going to tell the tubes that we're going to do crossfading between the tubes. We're going to do it at speed 4. We're going to go ahead and display a 6-letter word. We turn the tubes back off just to blank them and wait 2 seconds. And this call right here is the code we just looked at that picks a 4-letter word or 6-letter word, stages it and displays it. Have a function here that just displays the time on the tubes, and a function that does that scrolling effect for displaying the times on the tube. We kind of talked to these before. And that's really kind of the heart of it. We can look at this date names header function. Actually, we need to look at the C function for this. Date names just simply defines a bunch of arrays. So we have short month names, 3 letters. We have the long month names. We have the short day names and the long day names. We have an array here that's used for the first of the month, second, third, 25th day, etc. of the month. So that just defines those kind of features. We can look at the set time code here in a second. It's really probably the only thing we haven't looked at. Set time is rather involved. Actually, this code's no longer used. Why is that even in there still? Yeah, this code's no longer used. This is dead code. And none of these should be needed. Let me do. Oh, damn you. You see me keep doing it. I keep clicking where I want the cursor to be, and it doesn't end up there. Let me just do a quick test compile. I'm really sure these are no longer used, and they're not. I was using at one time a different interrupt to drive the setup before I encapsulated it back into just the one single interrupt. Includes various libraries we've looked at. This is the number of updates a second. So if you hold a button down to like increment the hours, it'll increment it 3 times a second. The workflow for this is all done through port A and these switch positions. So if port A switch 6 has been pressed, the interrupt handler will see that and call the time function here. And then when it's setting time, port A switches 0 to 5, increment or decrement, hours, minutes, seconds. If you push 6 again, it commits that and goes to the month set mode. 6 again, it goes to the weekday mode, and then it commits it to the RTCC. And really, this is just a long bit of nasty code that basically says, kind of falls in here. It throws out some debug. So you push the button down to set the time. The interrupt handler saw it and is called set time. And this says, wait for you to release that button right here. You release the button. Tube effects are off. Tubes are off. It scrolls by, set the time. It then shows you across the 6 tubes, hours, minutes, seconds, for 2 seconds, so you know which field is which. And then it basically says, well, that setup button is a 1. It's not been pressed. If we see button 0 down, we decrement the hours. We see button 1 down, we increment the hours. And there's just one of these little handlers. Then when button 6 here is pressed again, we know we've entered setting the time. It waits for 6 to be released. It does the same basic thing for the date. Same basic thing for the time. So it's just kind of brute force code to watch those 7 switches and set various things. Once you've got all the way through, it'll tell you to press startup. Set up to start. It's not actually set the real-time clock yet. It's waiting for that button to be released. Is this actually wait for a button to be released? It should actually be pressed. So we've released button 6. It's a 1. We tell you to press setup to start. We wait till it's been pressed. So while it's a 1, wait for it to be pressed. We then go ahead and set the RTCC time and date to the variables inside of that structure So what this code up here is actually doing is manipulating these two members in this structure. Again, the BCD values to the exact BCD values the registers will want to be. Tell us the time's been set. There's a couple of functions up here at the time I called pack. So pack time is basically taking where you've got the hours, minutes, and seconds in that structure set to, and it's packing it back down into the BCD encoded value that the RTCC would need to put into its register. Sets it, displays it, and does some debug information. I'm explaining this fairly poorly. But anyhow, this is really, I mean, it's pretty brute force, but this is how the time setting feature is implemented. And that's really, go ahead and compile, because I made a change in there. And didn't save it. So that's really it. As you can see, the C code really, the main code's pretty simple here. Initialize a few things. I've got my main master loop here that just loops forever. In this case, I've got 3 blocks of code in it that look at a particular bit on a port to say do 3 things, and that's really it. Everything else is happening in the background. The interrupt is firing, updating that structure. If I tell it to display the time, it'll just retrieve the time from that structure. In this case, I'm looking at the structure to say, has the time been updated? If it hasn't, nothing happens here. So once a second, this bit of code here will get ran. In the mode down here to drive the 6-letter word display. Another bit of code down here just to do that long scrolling time date function. So don't know if this has helped or hurt with my rather poor explanation of things here. This is written using the and actually wasn't where I wanted to go. Don't I have a version? So I'm using the Micro E, Micro C Pro for PIC32 compiler. I really don't want to show my about. Will get me where I want to go. This is version 4.0.0. I just downloaded this earlier today and installed on this machine and got the license key in. It's their latest version. I do have the VTFT module. I just haven't registered on this machine. I believe this code is pretty generic, that any C compiler for the PIC32 should really be able to deal with this. These are very standard names for the registers and bits, etc. in the PIC. If I do I'm trying to remember the key combination here. There it is. So Control-D here brings up this C library that really defines everything about that PIC processor, and these are all very standard names. So IVT core timer, these are all very standard names. I think they follow the microchip naming standards, and so everything I've written here where it touches registers inside of the PIC is really, it's using all these standard names. So I would expect this code to be pretty portable overall. If there's interest at some point, I'll get this kind of cleaned up a little further and load the library up at some point. There's not a lot of code here. It's taken a while to get things to work the way I want them to. Still not done with it. I've still got a case and things to assemble for it, and more code to add. But this is pretty much a quick update of where I am with the B7971 Clock project. So anyhow, I hope that wasn't too boring and maybe helpful to somebody. We'll talk soon.